All right, the topic today is capital budgeting. So up to this point, we've been thinking about how to find the value of cash flows, and finding the value of a cash flow that shows up today is very easy, right? $100 today is worth $100. It's very simple. And then we extended that framework to think about, well, what about $100 next year? And that would be $100. $100 next year is worth $100 next year, which is equivalent to some amount of money today invested at the risk-free interest rate. And so now we have a general idea about money arriving at different points in time, having different values based on prevailing interest rates. And then we applied that to some cash flow situations like mortgages and installment debt and retirement savings, things that paid us payments either forever or for a certain number of times, the same amount. And just kind of thought generally around, okay, if I have kind of whatever cash flows I have, I should be able to find the value of those cash flows kind of no matter what I get. And that's a good place to be, because now we're going to apply that kind of thinking to business projections. So if I have a business and I have forecasted things like revenues, cost of buying inventory, cost of rent and employees, taxes, that kind of thing. If I predict all that out, I will get some kind of estimate, a forecast of what I will be making if I launch this business or this project. And then we can ask a very reasonable question. If I undertake this project, what will the value of this project be to me? If the value is negative $1 million, then I can decide very quickly that I do not want to buy it. Right? I don't want to buy a negative $1 million project, and I would love to buy a positive $1 million project. So the value of a project itself can be inferred from the forecasted cash flows, and then a decision about whether or not to do it can be based on that value. That's capital budgeting. We're going to take our capital, right, our investment funds, and budget them according to what is valuable to do. So ultimately, we're going to come up with a decision of, should I do this idea or not? And whether I do it will depend on its value, and its value is hopefully positive. So that's just a summary of what we just talked about. So let's think about an example. So as I'm talking right now, I'm sitting in Wisconsin. So we have to break out an Oktoberfest example. So suppose I hope to sell custom Oktoberfest buttons using an $8,000 machine in my basement. Right, so, and there we go, throw that word in there. But this is, if you've ever attended Oktoberfest, at least around here, this is a thing. You buy big buttons and put them all over your shirt, and it's just all part of the fun. So I buy an $8,000 machine, and I expect to generate profits after taxes, costs, labor, and everything. And so taking away all the expenses, I'm going to have $2,000 left over every year for 20 years until I quit doing it. Okay, so $8,000 goes in, $2,000 comes out year after year after year. Okay, so the question is, does it make sense to put $8,000 on my credit card and buy the machine? It charges me 30% interest per year. Okay, so how can I know whether that's a good idea? Well, we can kind of make an eyeball guesstimate about whether it's a good idea. Right? If I pay $8,000 for this machine on my credit card, I'm going to pay 30% of that in interest in the first year. 30% of $8,000 is $2,400, right? 8 times 3 is 24. $2,400. So I have a $2,400 interest bill on my card and a $2,000 profit on my business, netting me negative $400. Okay, so Now, this project ends after 20 years, and we're not paying down the balance at all when we do it that way. So that just makes it worse. So we can already sort of intuit or surmise or predict that this will be a bad idea, that we shouldn't put this on our credit card. But what we want to do is find the actual dollar value of doing this Oktoberfest project. And so we can do that using methods from the last 2 weeks. So what we'll do is we'll say, okay, that $2,000 every year for 20 years, that's an annuity. We could use the annuity formula to do it, or we can use the financial calculator, which is the method I'll use because it's shorter. So if I go to financial calculator, all right, so here's the page at financialcalculator.com. So I'm going to clear these out, and let's start filling them in. Let's think about this. So I am getting a $2,000 payment, right? That's what I'm getting. $2,000 payment. I'm going to get it 20 times. The interest rate is 30%. Okay, now future value will be the lump sum I get at the end of my series of payments. And I'm not getting any lump at the end, right? I get 2,000 20 times and we're done. That's it. So there's no bonus cash at the end. There's nothing special. It just ends. Okay? So future value will be 0, and we're going to calculate present value. $6,631.59. Okay, so what does that mean? Well, if I put $6,600.31 on a credit card every year, I'd have some interest, and then my payment would pay it down and pay off a little bit of the balance, and so on until in the very last year, principal plus interest would exactly equal 2,000 and it would zero out. Right, so if my machine costs 6,631.59, it would zero out by the end of the 20 years. Right, it does not, right? This is an $8,000 machine. And so we can already figure out that this is a negative value proposition. In fact, it is negative to the tune of 8,000 minus 6,631.59. Okay, so don't buy the machine. That's the answer, right? Negative value, don't do it. What we just did was really just the same kind of thinking we've always done when we're finding the value of cash flows. But when we do it in this particular way, right, find the present value of all of the positive cash flows and subtract off the initial investment. When we do that, what we have done is an NPV, net present value net of initial investment. And when we do an NPV analysis, we can apply a decision rule. And the decision rule we apply is adopt all positive NPV projects. It's probably the most important sentence in all of academic finance. Right? Adopt all positive NPV projects. Why? Because if we have a positive NPV project, if we do the project, we generate value equal to the NPV of the project, assuming we've done it right. So if we adopt positive ones, we increase value. If we adopt negative ones, we decrease value. So don't adopt negative ones, skip those, only do the good ones, and the value of your company or wallet or personal financial situation will increase, or it'll get better. Every project with a positive NPV increases value by that much. That's NPV. So there's also another way to think about it, which is to say, well, what was the return we were getting on that Oktoberfest machine? What was the return we were getting on the Oktoberfest machine? So if I go back to here, right? So I'm going to say, well, what if I put 8,000 in there, right? It's an $8,000 machine. What return am I getting on my machine? And the answer is roughly 25%, a little 24.7%. And right away you can see the problem, right? If the project is paying us a 24.7% return, and financing charges us 30, now we have a problem, right? The returns from the project are less than the returns to the investors, and the difference has to be made up by us. That's bad. We're losing money. So that's a different rule. So this rate here, the rate that is that's the internal rate of the project, the return we would calculate, ignoring the market interest rate, is called the internal rate of return. And so we could come up with another decision rule that says adopt all projects where the internal rate of return, the interest rate of the project internally, is higher than the interest rate the investors demand. Right? If I'm getting 20% and they want 10, I make 10% and it's great. Right? So roughly, there's some compounding issue there, but that's 20. The 2010 is very close. And this is a great rule too. The problem is that getting this interest rate, the interest rate internal to the project, actually has some pitfalls and issues that come up frequently. Sometimes it's not as easy to calculate the interest rate as you might think. In fact, sometimes there are more than one interest rate that would make sense. And that's a real problem. So the best rule for that reason is the MPV decision rule, but the IRR decision rule, adopt all projects such that the internal rate is higher than the financing rate, is equally useful in some circumstances. Okay, so adopt all positive value projects or adopt all projects that have a greater return than your charge by your investors are both decision rules that make internal logical sense that we would view as consistent with what we've done already. Now, there are other decision rules that don't necessarily follow the logic of the rest of this course so far that do get used but have some problems. So the classic one, and I've encountered this in the wild for sure, is the payback rule. So the payback rule is how long does it take to get your money back if you invest in a project? So I encountered it doing some consulting work with some apartments. They were looking about, they were deciding whether or not to replace the boilers in the apartments. And boilers, if you don't know what a boiler is, it takes energy and boils water, turns it to steam, and that steam is used to heat apartments and buildings and stuff. So it's just an energy transfer device, and it's pretty much just kind of like a giant metal bubble that boils water. So they're very simple, but I mean the technology has improved slightly over time. And so they can be a little more energy efficient now. And so if the apartments were considering replacing the boilers to get the extra energy efficiency, which would save money because you would spend less on fuel costs. But they calculated it out, and it would take about 18 years to get the money back. So yes, eventually you get your money back, but it would take 18 years to get there. And in their mind, that wasn't enough to justify purchasing the boiler. Now, we could do the same thing with NPV, right? You would say, okay, what's my annual savings in fuel costs, and what's my annual interest cost on the money I invested in this boiler? And if the interest cost is higher than the fuel savings, then it doesn't make sense. So the payback rule is a lot easier to calculate, right? You just take the dollars in divided by the dollars in divided by the dollar savings per year and get some number, and that's how many years it takes to pay back. But obviously there's some pretty significant problems with that. First, it ignores any cash flows after the payback. So for example, you might have a mine where you dig a mine it for a couple years, and then spend a ton of money cleaning it up. Well, you'll get a really fast payback, but it still might be a negative NPV project. If the cash flows are decreasing, even if it pays back, it may not pay back that the money after the payback period may not produce enough money to push it to positive NPV, and the earlier years, while maybe somewhat lucrative, don't take interest into account. And so that's a big problem with payback, is we're not doing time value of money at all, and therefore we can have a payback but not payback soon enough to be positive NPV. And that's a problem, right? So we don't want to adopt a project that has negative value just because the payback is low. And so that's why when people use the payback rule, they usually set some kind of hurdle rate that's relatively short, but that doesn't resolve the problem. Again, because time value of money is still being ignored, and occasionally that will cause trouble. But there are certain very narrow circumstances where the same kind of project can look very, very similar, and so you could do an analysis of, say, an NPV analysis of one, show what payback would have to be positive NPV, and then recycle that payback rule for very similar projects, just as a rule of thumb. So it's useful as a rule of thumb, and that's about it. Okay, so now let's do a different one. So we have a different example. So what if I front load some of the money here, right? So I make 6,000, 4,000, 2,000, and 1,000. So now, don't forget, before we had 2,020 times, so that was $40,000, and now we're only making 13. So the dollar value I'm getting now is much smaller, but we're getting it much earlier, and so we're going to see whether we end up ahead or behind. So let's go ahead and try it, and I have the answer here, right? It's 242.71. So we've got 6,000, 4,000, 2,000, and 1,000. Oop. Here we go. So 6,000, 4,000, 2,000, and 1,000. And here, let me zoom in a little bit. Oh, enter, then zoom. Okay, there we go. All right, so this is year 1, 2, 3, 4. And we have our interest rate, right? Our R is 30%. Okay, so there's a couple different ways we can do this. So let's do a present value calculation. So 6,000 divided by, so the present value formula is 1 plus R. Now this is a data cell, so I'm going to push F4 or Command T and lock it in. And then to the power of 1. I'm not going to lock that in, or the 6,000, because I want those to change as I slide it. All right, so right away, the 6,000 is actually only worth 4,600 because we have to pay a bunch of interest on the credit card to get it. So we'll extend these to here. I can sum. Right, and so so this is the present value of the cash flows, and our NPV would then be this minus the initial cost of 8,000. So there's our 242.71. We can also use the NPV function. You give it a rate, and then you draw a box around the cash flows. Oops, wrong box. Right here. You put it around the unadjusted cash there. There we go. Same number, right? Same number. So we could subtract 8,000 from that as well and get to the same place. Okay, so there we go. So there's our that's an NPV right there again. Same NPV, just using the NPV function in Excel. So what's better, getting 13 early or getting 20 over 20 years? And the answer is at 30%, getting 13 earlier is better. Right? In fact, we would actually do the project here, and we wouldn't do it in the different version. Okay? So that's just a simple example of an NPV. So when I'll stop the video, and when we come back, We'll do some more examples, and then look at some other we'll look at the other decision methods, including IRR, payback, and discounted payback.